Black holes. Just the name sparks curiosity and a hint of fear. These enigmatic entities have fascinated scientists and the general public alike for decades. They are regions in space-time where gravity is so strong that nothing, not even light, can escape. This immense gravitational pull is due to the collapse of massive stars leading to a point of infinite density known as a singularity. Imagine a place where the very fabric of our universe collapses in on itself. This warping of space-time creates a gravitational well so deep that escape becomes impossible. A place of infinite density and immense gravitational pull. The boundary around this region is called the event horizon, beyond which nothing can return. These cosmic monsters lurk in the darkness of space, silently shaping the cosmos around them. They influence the orbits of stars and the formation of galaxies, playing a crucial role in the evolution of the universe. For centuries, black holes were merely theoretical constructs, mathematical curiosities predicted by Einstein's theory of general relativity. Einstein himself was skeptical about their existence, but today we have compelling evidence that these enigmatic objects are very real. Advanced telescopes and observatories have provided us with images and data that confirm their presence. We see their gravitational influence on nearby stars and gas clouds. Stars orbiting an invisible point in space, moving in ways that can only be explained by the presence of a black hole. We detect the powerful X-rays emitted as matter swirls around their edges, heated to millions of degrees. This high-energy radiation provides a window into the extreme environments near black holes, allowing us to study their properties and behavior in unprecedented detail. How do these gravitational behemoths form? The most common type, stellar mass black holes, are born from the death throes of massive stars. Stars much larger than our Sun. These stellar giants live fast and die young. When they exhaust their nuclear fuel, they can no longer support their own weight. Gravity takes over, and the star collapses in on itself. This collapse triggers a supernova, a cataclysmic explosion that can outshine an entire galaxy for a brief period. If the star's core is massive enough, the collapse continues unabated. It crushes the core into an infinitely small point called a singularity. A black hole is born. Surrounding the singularity is an invisible boundary known as the event horizon. This is the point of no return. Once something crosses the event horizon, it can never escape the black hole's gravitational pull. Not even light, the fastest thing in the universe, can break free. Think of a waterfall. The water flows inexorably towards the edge. If you're far enough away, you can swim against the current and escape. But once you're swept over the edge, there's no turning back. You're destined to plunge into the depths below. The event horizon is like that waterfall, a boundary in space-time beyond which escape is impossible. Now imagine we could send a camera on a one-way mission to a black hole. What would it see as it approached this cosmic abyss? As our intrepid camera drew closer, the black hole's immense gravity would begin to warp the fabric of space-time around it. Light from distant stars would be bent and distorted, creating strange swirling patterns. The camera itself would experience time dilation, a consequence of Einstein's theory of relativity. As the camera neared the event horizon, time would slow down for it relative to us back on Earth. From our perspective, the camera would appear to move slower and slower, its image redshifting until it faded from view. Section 5. G-forces and time warps. Extreme physics at play. Gravity is a force that pulls objects towards each other. It's the invisible hand that keeps planets in orbit around stars and moons around planets. The more massive an object, the stronger its gravitational pull. This is why massive planets and stars have such a significant influence on their surroundings. Black holes are so dense that their gravity is incredibly strong. They are formed when massive stars collapse under their own gravity, creating a point of infinite density. This intense gravity has some bizarre effects on space and time. The fabric of space-time itself gets twisted and warped in the presence of such immense gravitational forces. Time dilation, as we mentioned, is one such effect. Near a black hole, time slows down dramatically compared to regions farther away. Imagine time as a river. In the vast expanse of space, this river flows at different speeds depending on the gravitational forces at play. Near a black hole, the river flows much slower. This means that if you were to observe someone near a black hole, their movements would appear to be in slow motion. Another effect is called spaghettification. This occurs because the gravitational pull is so much stronger at one end of an object than the other. Imagine yourself falling feet first towards a black hole. As you get closer, the difference in gravitational pull between your feet and your head becomes extreme. The gravity at your feet would be much stronger than at your head. This creates a stretching effect, pulling you apart. This difference in gravitational pull would stretch you out like spaghetti. It's a dramatic and somewhat terrifying demonstration of the power of gravity in extreme conditions. Black holes continue to fascinate scientists and astronomers as they push the boundaries of our understanding of physics. They are the ultimate laboratories for studying the laws of nature. At the center of many galaxies, including our own Milky Way, lies a supermassive black hole. These cosmic giants play a crucial role in the formation and evolution of galaxies. As we continue to explore the universe, black holes remain one of the most intriguing and mysterious phenomena, challenging our understanding of space, time, and gravity. Section 6. Spaghettification, stretching to the limit. As our camera drifted closer to the event horizon, the difference in gravitational pull between its near and far sides would become increasingly extreme. This tidal force, known as spaghettification, would begin to stretch the camera, elongating it along a radial axis pointing towards the black hole's center. The camera's internal components would be subjected to immense stress as the relentless tidal forces pulled them apart. Eventually, the camera would be ripped to shreds, its atoms themselves torn asunder as it crossed the event horizon, lost forever to the insatiable maw of the black hole. Section 7. Beyond the Veil. What happens inside? What happens inside a black hole remains one of the greatest mysteries of modern physics. Our current understanding of physics breaks down at the singularity, the point of infinite density at the heart of a black hole. Some theories suggest that black holes could be gateways to other universes or dimensions. Others propose that information about everything that falls into a black hole is somehow encoded on the event horizon, preserved like a cosmic hologram. The truth for now remains shrouded in the enigmatic darkness of the black hole itself.